Welcome to the online video lecture series for intermediate algebra at Wayland Baptist University. We're ready to start Chapter 4. My name is Dr. Scott Franklin. I'll be leading you through these lectures. In Chapter 4, we're going to now talk about something called inequalities. Whereas we have dealt with largely equations in previous chapters, we need to also address how we solve mathematical expressions which involve inequalities, meaning that one expression is not equal to another, but we know somewhat of the relationship between the two in terms of its inequality. For example, one may be less than the other, greater than, less than or equal to, or greater than or equal to. So we need to be able to solve these types of problems that involve inequalities, and that's what we're going to be doing here in Chapter 4. To begin with, in Section 4.1, we're going to solve linear inequalities, just basic single linear inequalities. As we move further into the chapter, we will look at combined inequalities or compound inequalities, and we'll also look at systems of inequalities, just like we looked at systems of equations. But we're going to start with the basics. We're going to start at the very beginning and talk about how we solve linear inequalities. Now, it turns out, once we understand what an inequality is and how a linear inequality looks, solving them is going to be almost exactly like solving linear equations, with one extra little caveat, if you will, and we will cover that in detail in this section. In this section, we're going to graph an inequality solution set. We're going to use set builder and interval notations. We're going to solve linear inequalities and then express our solutions in those techniques that we've just covered. We're going to recognize inequalities that may have no solutions or all real numbers as solutions. And we're going to solve applied problems using linear inequalities. In your notes, you have the following table. You have this table of linear inequalities. What I want to do is I want to fill this thing in looking at the different types of solutions that we can get from a simple linear inequality. So these are all the types of solutions that we may get, and you'll begin to see the pattern as we go through this. First of all, the most common interval type solution would be a solution that would look like the interval from A to B. So let's start off by assuming that A and B are two real numbers. So on some real number line, we have the number A, which is less than the number B. Okay. Now, if we have the interval A comma B, now in this context, and you're going to have to tell this from what kind of a problem you're working on, and this looks like an ordered pair, so it looks like a point, but in the context of talking about intervals, this notation means the set of all numbers, in fact I can write this as a set, the set of all numbers x, such that x is some real number between A and B, but not including A or B. So if I were to graph this on the real number line, it would look like this. I would put parentheses at A and B pointing towards each other, meaning that I'm not including A and I'm not including B, but every number in between is an element of this set. So this represents the set of all numbers from A to B. Okay? Another type of interval we might see is the same set that we just saw, except include A and B. A, B. So let's say it's all the numbers in between A and B, but also including the endpoints. Okay? And I would indicate that with a bracket notation. If I write a bracket, that means include the endpoints in that interval. So this is the set of all numbers. I'm just shading in between these two numbers. You can shade however you like, but I'm shading from one to the other. I'll typically use my little squiggle notation. But from A to B, including the endpoints. And we would write that as an interval as A comma B with brackets on either end, or if we used our set builder notation, we'd write it as the set of all x, such that x is between, meaning bigger than or equal to A, less than or equal to B. There's the set builder notation for that type of interval. The next type of interval may actually include A but not B, or include B and not A. So we have these two types of sets. they would either be called half open or half closed, right? Both of those terms are accurate for both of these intervals. So what would the first one represent? Well, it includes the set of all numbers from A to B. It includes A. So we have a bracket here. And it does not include B. So it's all the numbers in between there, including A, but not B. And if we were to write that as a set interval or a set builder notation, x, set of all x such that A is less than or equal to x less than B. Similarly, the interval from A to B included, would not include A, so it would be an open interval or a parenthesis here and a bracket here. That set of numbers, which we would denote in set builder notation as a set of all x such that A is less than x is less than or equal to B. Okay? So these are all the types of intervals that you might have where you have going from one number to another. Another type of solution that we'll get, and actually these turn out to be a little bit more common in the examples we're going to be looking at, is what if I was considering on the real number line every number bigger than A. That is, start at A, don't include it, but go bigger than it and keep going. Right? That is, the set of all x such that x is strictly bigger than A. Right? We've seen these kind of inequalities earlier in this course. That just means start at A and keep going, shade all the way to the right. I would write that as an interval the following way. I would say, okay, open parenthesis, start at A, but where does it end, right? These other ones up here all ended at B. This one doesn't end. It keeps on going forever. And this going on without bound in mathematics, we denote using the infinity symbol, which is a sideways 8. This is just another way of writing the set of numbers that starts at A and keeps on going to the right. Okay? And since you can't include all of infinity, right, because infinity goes on forever, infinity is not a number, I will put an open parenthesis anytime I have infinity in my interval notation. Just another way of writing it. 3 different ways of writing the solution. Okay? I can also write it as A included in the set and going on to infinity, or the set of all x such that x is bigger than or equal to A. If I were to graph that on the real number line, it would look something like this, right? Graph, here's A. I would just put a bracket at A and shade everything to the right of it. And similarly, we have, these are greater than. What if we had less than or equal to? Well, we would have something that looks like this, right? We would have the set of all x such that x is, say, less than b, which I think everybody in here by this point should be able to graph that on a number line. You just go down here and put where b is. Say b's right here. I'm saying all the numbers less than b, so that doesn't include b. So put a parenthesis and shade everything to the left. That's the graph of that set. Now, how do I write that using interval notation? Well, since the right-hand endpoint is b, I'll put b here and put an open parenthesis because it's not included. And where does it go as you go to the left? Well, it keeps going forever. Now, I'm not going to put infinity there because infinity meant going everywhere to the right, keep going to the right. So to mean keep going to the left and never stop, I'm going to put negative infinity and also never include it. Similarly, I could go from negative infinity up to b and include it, which would look like the set of all x such that x is less than or equal to b, and graph this in the following manner. Here's b, so it would be a bracket at b and shade everywhere to the left of it. Alright, so looks like I've got all possible inequalities, right? Except for what happens if there's no endpoint, right? What if I consider, oh, we don't want red. What if I consider all of the number line? That is, the graph of it being shade the whole line, all the way from left to right. as a set builder notation, I would write it like this: the set of all x such that x is any real number. X is an element of the set of real numbers. If I wrote it as an interval, it'd be from negative infinity to positive infinity, meaning include every single number. Alright, so these are all the possible types of solutions that we can get. We can get intervals that have an endpoint on each end, either included or not included. We can have half interval or half number line, right, from A up or A to the right, included or not included, or from B down or B to the left, be included or not included, or we can have the entire number line. We're going to want to be able to graph any of these types of solutions. We're going to want to be able to write them in set builder notation and be able to write down their interval notation. It's usually easiest to start with the graph and then figure out what the other two notations are from that graph. So let's say that we're asked to graph the solution of each of these two inequalities on a number line and then write down the solutions in set builder notation and interval notation. Now these are already solved for us in terms of x, so x greater than negative 4, if I wanted to graph that on a real number line, I'd start by graphing or drawing my real number line and then plot some points on there. I need to go from negative 4 to the right because I want all numbers bigger than negative 4. So here's 0, 1, 2, 3, 4. Go an extra one for just good measure. Label them. So all numbers greater than negative 4 would mean starting at negative 4. So put a parenthesis here and shade to the right, and there's no endpoint on the right, so just keep going. So there's the graph. Set builder notation is just the set of all x such that, and then rewrite your inequality, x greater than negative 4. Interval notation just writes it in terms of its left and right endpoint. Its left endpoint is negative 4, but not included. Its right endpoint, there is none, so it goes on forever, is infinity. So here's your graph, here's your set builder notation, and here's your interval notation. Let's do the same thing on example B. Start by graphing this on a real number line. So I need to go from at least negative 2 up to 7. Let's put 0 here. 1, 2, 3. So here's negative 1, negative 2, negative 3, 1, 2, 3, 4, 5, 6, 7. So it goes from negative 2, and because that's less than or equal to, it means it includes negative 2. I'll put a bracket there. Up to 7, inclusive, so put in a bracket there, and every number in between is shaded. There's your graph. Your set builder notation, usually that's the easiest once you have the solution set. Once you have the inequality solved for x, in this case, just write down the inequality, negative 2 less than or equal to x less than or equal to 7. Okay? And then the interval notation goes from negative 2 up to 7, and it includes both of them, so I put brackets around it. And there you go. That's the graph, the solution in set builder notation and in interval notation as asked for. Now let's lead up to how we actually solve inequalities. The above problems that we just did in those two examples actually had it already solved for us, already had the x by itself, but in some cases the x may not be by itself. Take a look at this example right here. 2x plus 3 is less than 7. I can't graph that immediately. I have to figure out a way to get x by itself. So there's a couple of properties that inequalities have that we need to make use of. The first one is the addition property, which is going to be familiar to you because we use this exact same property with equations. It works both in equations and inequalities. That says if A is less than B, then A plus C is less than B plus C, no matter what C is. What did I do? I added C to both sides. I can add the same number to both sides and the inequality stays the same. I can also subtract from both sides and I get also an unchained or equivalent inequality. So the property in words says if the same quantity is added to or subtracted from both sides of the inequality, the resulting inequality is equivalent, meaning it has the same solution set, to the original one. Now, how would we use that? Well, think about how you would solve this, right? You wouldn't get the x by itself. You would move the 3 to the other side. Because of the addition property, you can subtract or add a negative to both sides. We're going to subtract 3 from both sides here and get the x term by itself. And as you'd expect, the next step you'd want to take is to be able to divide both sides by 2. So we need a property that says we can multiply and divide both sides by the same number as well. Well, we have something called the positive multiplication property. Of inequality. Now, why is it called the positive? Well, it's because I am required for the following statement to be true that I have C be positive. Okay, that is A is less than B is given. I'm going to multiply both sides by the same number. As long as C is positive, that's true. If C is negative, that's a false. That's not going to be true. It's only true if C is positive. And I can also divide both sides by C, and it stays the same. Inequality stays true as long as C is positive. So the property in word says if we multiply and divide both sides of an inequality by the same positive, meaning greater than 0, not negative, doesn't have a negative sign on it, the resulting inequality is equivalent to the original one. So notice how we can make use of this. This is where we got to in the last problem. We had 2x is less than 4. If I want to get x by itself, I can divide both sides by 2. 2 is a positive number, so the following inequality is in fact true. Now, what happens if I had, say, negative 2x is less than 4? Can I divide both sides by negative 2? Right? What do I do then to get that x by itself? Well, you use something called the negative multiplication property, which says that if you want to multiply both sides by a negative, you want to take A and B and do A and C, so AC and BC, and compare those, that the sign must switch directions for that to be true. And if I want to divide both sides by a negative number, the sign has to switch directions. In fact, the fact that I have to flop the sign over makes me call this this is my own word for this, but I call it the flop rule. Meaning I'm going to flop the sign over whenever I multiply or divide both sides by a negative number. So the property in words says that if we multiply both sides of an inequality by the same negative quantity and reverse the direction of the inequality symbol, the resulting inequality is then equivalent to the original one. So in this example, if I had negative 4x is less than 20, I want to divide both sides by negative 4. Notice how the sign must change directions for that to be true. Okay? That's the flop rule. If I want to multiply or divide both sides by a negative, the sign must change directions. Okay? Now, I want you to notice why this has to be true. We're basically taking a shortcut to keep the x on this side. Notice I could equivalently solve this problem a slightly different way. If I have negative 4x is less than 20, what if I added 4x to both sides? Right? I end up with 0 is less than 20 plus 4x. And then subtract the 20 across. I have negative 20 is less than 4x. Right? Now divide off the 4. And what do you end up with? You have negative 5 less than x. Right? Notice how x is on the bigger end of that inequality. this is the same thing as this, right? X is on the bigger end of that inequality, right? Dividing by a negative and remembering the flop rule is a shortcut so that we don't have to go through this whole process and then get here and then flip the whole thing over on its side. Okay? So that's what you got to remember. It's exactly going to be the same technique we use for solving equations to solve inequalities, with one exception, and that's this property 3. Whenever we use a negative to multiply both sides or divide both sides, we have to change the direction of the sign. Just to recall, let's go through the steps that we use to solve those types of things. So we'll have the steps here available to us as we work a few of these problems. We're going to start by simplifying the algebraic expression on each side. Then we use the addition property to collect all the variable terms on one side and all the constant terms on the other. Get the variable term by itself. Next, we're going to use the multiplication properties. Okay, meaning that we actually have two of these. We got the multiplication property for positives and for negatives. In other words, we need to remember the flop rule. But that gets the variable by itself. That takes the coefficient off of it, thus solving the inequality. And once we get done, then we go back and use what we just covered at the very beginning of this section and be able to write the solution in set builder notation or interval notation, depending on what is asked for or needed in that context. And of course, we need to be able to also graph the solution set on a number line. Let's look at an example where we go through these steps. Let's solve the following linear inequality. And by the way, I have a typo here. In your notes, change this sign from equals so that it says 3x minus 5 is greater than 17. So the problem is 3x minus 5 is greater than negative 17. Okay? To solve that, we get the x term by itself, which means we can move this 5 across to the other side. So add 5 to both sides, and I'll have 3x is greater than negative 12. Now, divide both sides by 3. And always ask, when you multiply or divide, do I have to change the direction? I do not have to flip the sign, so I end up with x is greater than negative 4. We are asked to graph the solution on a number line and write the answer in both set builder and in interval notation. So to graph it on the number line, I start by graphing my number line. Here's 0, go to 1, 2, 3, 4. Here's negative 1, negative 2, negative 3, negative 4. Greater than 4 means this direction, shaded to the right. The set builder notation would be the set of all x such that, and then just write the solution inequality, x greater than negative 4. If I write it as an interval, easiest to look at the picture to see the interval. It starts at negative 4 but doesn't include it and goes all the way up to positive infinity. So there are your 3 versions of the solution set. Let's do a few more examples. Step 1 says to simplify each side, so I'm going to begin by multiplying the right-hand side of this problem out. 5 times 3 is 15. 5 times minus x is minus 5x, less than or equal to 3x minus 1. I want to get the x's on one side and the numbers on the other, so I'm going to start by moving the 15 across, subtract 15 from both sides. I have negative 5x is less than or equal to 3x minus 16. Let's move the 3x over, so subtract 3x from both sides. Now when you're subtracting, you don't have to worry about sign change. You can add and subtract all day long. It doesn't change the sign. I have negative 8x is less than or equal to negative 16. So now I'm going to divide both sides by negative 8. Do I have to change the direction of the sign? Yes, I do. I have to flop it, okay, to get x is less than or, no, x is greater than or equal to 2, because negative 16 divided by negative 8 is positive I had to flop because I divided by a negative. Graph it on a real number line. X is greater than or equal to 2 means go to 2. And go greater than or equal to, meaning include the 2 and go greater. Okay. That's the set of all x such that x is greater than or equal to 2 in set builder notation. And as an interval, it starts at 2 and is inclusive and goes to the right to infinity. And there's your final answer. Alright, same thing in this example. Start by simplifying both sides. There's nothing to simplify here, so we are going to get the x by itself. I'm going to subtract x from both sides and end up with a minus 3x minus 4 is greater than 5. I'm going to add 4 to both sides to get minus 3x is greater than 9. Now I divide both sides by negative 3. Now I'm dividing by a negative, so I flip. I'm going to end up with a less than instead of a greater than. X is less than negative 3. So on the real number line, go to negative 3. Here's 0, 1, 2, 3. Negative 1, negative 2, negative 3, negative 4. Less than means going to the left. Not included because there's not or equal to. And shade all the way down because there's no left-in point. That means the set of all x such that x is less than negative 3 is your set builder solution, and your interval, where does the left-in point? It doesn't have one, so it's negative infinity all the way up to negative 3, but not including it. And there is your solution. On this next example, we do need to simplify the right-hand side, so I'm going to start by multiplying that out. I end up with 5x is less than 5x minus 15. Now to move the x over, I'll subtract 5x from both sides, and you'll see something happen here that hasn't happened before in this section. 5x minus 5x is 0, is less than, it cancels out there, negative 15. All the x's canceled out. Now we've seen this happen before. We saw it happen in equations and even systems of equations. When the x's drop out, that means we have a special case. We're not going to get a unique solution, or we're not going to get the kind of solutions that we expected. So what do? Well, we always ask, what's the truth value? Is it true or false? Right? Is 0 less than negative 15? Is 0 to the left of negative 15? And the answer is no, it's not on the number line. It's actually bigger than. So this is false. Okay? Which means the solution is actually no solution, or equivalently we can write it as the empty set. So when the x's drop out, always check and see whether or not it's true or false. If it's false, you know it's going to be no solution. Alright, let's do another one. The next one, simplify first on the initial step. So we get 2x plus 8 is greater than 2x plus 3. Same thing's going to happen here, isn't it? We got a 2x on both sides. What happens is I try to move the x's over. They completely cancel each other out. I'm left with 8 is greater than 3. Notice how that's a true statement. That says that no matter what x is, in the original problem, it's always equivalent to a true statement, which means every value of x is a solution. All real numbers. Now, for the all real numbers case, we can actually still do all three of our versions of the solution. Right? We can graph it on the real number line. Right? It's just shade the whole line. You can write it as a set builder notation. We did one of these on the very first page of your notes in this section. And you can also write it as an interval from negative infinity to positive infinity, not including the infinities because you can't. That would be the solution. All real numbers are the solution to this, but there are three different ways of writing all real numbers. Alright, now let's take a look at some applied problems. One of the things you're going to want to be able to do is translate some key phrases into inequalities. Now, we've done this a little bit. You know how to translate directly things like this number is less than, or is greater than, or is less than or equal to, or is greater than or equal to. Those are just direct translations into the symbols that represent those concepts. Sometimes you'll see phrases like these: x is at least 5, and I want you to be able to write down that as an inequality. And really the key is to think about what kind of numbers satisfy that statement. Right? What numbers could I put in for x that would make that true? Now, if I said x is at least 5, right? At least 5 means something at 5 or bigger, right? 6 is at least 5. 7 is at least 5. Okay, in fact, 5 is at least 5, because at least 5 means at the very least it could be 5, but it's going to be more. Okay, so if I wrote that as an inequality, it would be x is greater than or equal to 5. Now, what about at most 5, which means it can't be bigger than 5? That would mean that x needs to be less than or could be equal to 5, and that's how we would write that as a mathematical statement. All right, now to say x is between 5 and 7, we've seen this before with some of the graphs that we've drawn. Between actually looks like it if you do it this way. X is between 5 and 7, meaning x is bigger than 5, or 5 is less than x, and x is less than 7. Okay, x is between 5 and 7, I would write this way. All right, the next one. X is no more than 5. No more than. That's actually the same as saying at most 5. No more than 5. So that's x is less than or equal to 5. And if I said no less than 5, would be something has to be bigger than 5. It could be equal to 5 because 5 is not less than 5. So x is greater than or equal to 5. That's how we would translate these types of statements. Now let's look at an example where we might have inequalities as the type of model that best describes the type of question we want to answer. You are choosing between two long-distance telephone plans. Plan A has a monthly fee of $15 with a charge of 8 cents a minute for long-distance calls. Plan B has a monthly fee of $3 with a charge of 12 cents per minute for long-distance calls. How many minutes of long-distance calls in a month make Plan A the better deal? Okay, let's start with the most reasonable questions. What do we want to let our variable be? What's the missing piece here? Well, we're asking for how many minutes, so let's let x be that. X be the number of minutes used in long-distance calls. Alright, so in terms of x, how much does Plan A cost? Right, it's $15 with a charge of 8 cents per minute. So that's 15 plus 8 cents per, meaning times the number of minutes, which is our unknown. Plan B cost is a $3 fee and then 12 cents per minute. So it looks like this. Now we want to know when Plan A is the better deal. Now better deal means it costs less, right? So we want to know when is Plan A less than B, right? That's what the better deal would mean. So we want Plan A cost less than Plan B cost. So that looks like this. It would be 15 plus 0.08x less than 3 plus 0.12x. Now I've got an inequality in terms of x. I can solve using our techniques. Simplify both sides. That's done. Let's get the x term by itself. So I'm going to subtract 15 from both sides. I get 0.08x is less than negative 12 plus 0.12x. Just subtracting 3 minus 15. Now let's subtract the 12 or 0.12x from both sides. I get negative 0.04x is less than negative 12. Now divide both sides by the coefficient of x, negative 0.04x. Okay, I'm dividing, so, and by the way, I don't want to divide off the x. Sorry, that was a careless mistake. I want to just divide off by negative 0.04. Now, do I flop it? Do I flop the sign? And the answer is yes, I do, because I'm dividing by a negative. I get x is greater than negative 12 divided by negative 0.04 gives me 300. So x needs to be bigger than 300. Now what is x? X is the number of minutes. So for plan A to be the better deal, we need our number of minutes to be more than 300. So plan A is a better deal if we use more than 300 minutes. Okay? And that would be the answer to that. Okay? And that's it. That's the end of section 4.1.